Welcome to the Statistics Informed Decisions Using Data lecture video. This lecture video is going to be based on Chapter 1, the Data Collection Chapter, and we are going to be working out of the 6th edition of the Statistics Informed Decisions Using Data textbook. And this is for Professor Thomas's Math 146 Introduction to Statistics course. So first we're going to look at some of the learning objectives from Chapter 1. And there are 5 different learning objectives, and these are probably going to be in your notes as well, the outlines of our class notes. I have provided a location for those in the discussion section of our Canvas class, so be sure to print those out. You might want to add to them, maybe work off of the Word document, however you want to do it. Keep in mind, as you prepare to tackle the practice problems, you might want to gloss over the chapter from the textbook. And so we have different versions of the textbook, and any version should be sufficient. All right, so first we're going to define what statistics and statistical thinking really is. The process is going to be explained, and then consider the difference between qualitative and quantitative variables. So data can come in all forms. There's qualitative data like eye color, race, gender. Those are qualitative variables, and quantitative variables are more like numeric type of values like age, weight, things of that sort, things that can be quantified. Distinguish between discrete and continuous variables. The truth is there's numbers can be divided into many different categories. Discrete numbers are whole numbers, where continuous numbers are decimal numbers, approximated numbers, values for like your weight, your height. Those are only as precise as the instrument that is used to measure those devices. The truth is no one really knows your true weight, or no one really knows your true age. If you measure it out to the nearest millisecond or nanosecond, or if you measure your weight out to the nearest 100,000th of a pound, it's going to vary. You're going to get a string of random digits at some point. Discrete numbers are those numbers, like if we were to ask you the number of eggs in an egg carton, there should be a discrete number of them that you can count. And then finally, determine the level of measurements of a variable. And those are 4 different levels of measurement. And all numbers can be divided into those 4 levels of measurements. So first, let's look at the first objective. And basically, it's just the science of collecting, organizing, summarizing, and analyzing information to draw conclusions or answer questions. And then I like how they say that statistics is about providing a measure of confidence in any conclusion, because we can never be 100% certain, but we can quantify and measure our level of certainty, so much so that we can pretty much determine if something is likely to happen or not based on our statistical methods and conclusions. Here we have the information referred to, and the definition is data, and data are a fact or proposition used to draw a conclusion or make a decision. All right. A key aspect of data is that they vary. So, the question is everyone in your class the same height? Does everyone have the same hair color? So there is variability. Here we have data vary when measured on ourselves as well. Do you sleep the same number of hours every night? No. Do you consume the same number of calories every day? No. And one goal of statistics is to describe and understand the sources of variability. Absolutely. Because if we understand how wide things vary, we can now make predictions that are very precise. But again, statistics is the science of collecting, organizing, summarizing, and analyzing information to draw conclusions. And the information is indeed data. Objective 2 is to explain the process of statistics. And so really, we normally work with samples. I mean, it's usually understood that whenever you're making calculations, you're working with a sample of some larger population. That's kind of the thing that's unsaid in statistics. Okay. The entire group of individuals to be studied is called the population, and that's when you get a consensus. An individual or person of the object that is a member of the population is being studied. A sample is a subset or a group from the population. Usually it is a random group, and we do that to eliminate certain biases in our studies when we get samples. It's very important that our sample is a good sample, a good representation of the entire population. There will always exist bias, but as we study and learn, we can control the bias, we can account for it, we can expect it. And even in artificial intelligence, even the machine can be biased, and there are bias variables that need to be controlled and parameters that need to be um, calibrated to weed out bias at all levels. So here, a statistic, not to be confused with statistics, but a statistic is a numerical summary based on a sample. So if we had a sample, you calculate the mean of the sample. Let's say we did a sample of our class, we took half the students out of our class and we decided to calculate the average age of a sample of our class. All right, so suppose our class has 30 students in our class and we decided to pull out 10, randomly selected 10, and we calculate the average age of the sample. That calculation is a numerical summary, and that's actually would be a statistic, the value that we get. We might do that, calculate that, and we might get, say, 22.5. That would then be considered a statistic. Descriptive statistics consist of organizing and summarizing data. So descriptive statistics, sometimes we also call this exploratory analysis. So if we have numbers, not only do we calculate the mean, but we do a lot of other things. We may calculate the mean, median, mode, and graph the ages of the sample. And we're just trying to organize it and summarize it and make sense of it, calculate the range of values and all of these other things. So, um, you know, descriptive statistics is one part of statistics. There's another part of statistics called inferential statistics. And usually most statistics courses is divided. The first half, up until about the midterm, you're really dealing with exploratory analysis or descriptive statistics. And then in the second half of the course, you're more dealing with inferential statistics, which, as you can see, the method here says it uses methods that take results from a sample and extends them to the population and measures the reliability of the result. So a parameter is a numerical summary of a population. So a statistic is to a sample as a parameter is to the population. Let's look at an example here. Okay. Here's our example. It says suppose 48.2% of all students on your campus, this is of all students, own a car. This value represents a parameter because it is a numerical summary of a population. Suppose a sample of 100 students was obtained, and then from that sample we found that 46% own a car. This value represents a statistic based on its numerical summary. All right, the process of statistics. So let's look at the process. So the first step would be to identify the research objective. Second step, collect the data needed to answer the questions posed in the first step. And again, you do have to be meticulous when you are collecting data. There are many ways to collect data. Oftentimes, there may be errors at this step. There could be bias happening at this step. And when we collect data, we do want to be careful about collecting data that is biased. Next is to describe the data. So this is where we get into the descriptive statistics. Perform inferences. Okay, so we apply certain statistical tests to our data. And that will then allow us to make either predictions or to report a level of reliability of our results. And as you can see, the techniques for measuring reliability are in chapters 5 through 8, and the inferential techniques are in chapter 9 through 15. Let's look at an example here now. In this example, we're looking at the process of statistics, trust your neighbor. So Pew Research conducted a poll and asked, do you trust all or most of your neighbors? The following process allowed the researchers to conduct their study. First, identify the research objective, collect the data needed, describe the data, and there's the fourth step there would be to perform the inference. All right. So as you can see, in the very end, they were able to calculate this 2.5% margin of error there. All right. Let's look at the third objective, and this is where you need to distinguish between the qualitative and quantitative variables. So variables are the characteristics of the individuals within the population. All right. One thing to note is that variables do vary. Consider the variable weight. If each tomato had the same weight, then knowing the weight of one tomato would allow us to determine the weights of all of them. Or the weights of tomatoes vary. One goal of research is to learn the cause of the variability so that we can learn to grow plants that yield the best tomatoes. Qualitative, or sometimes we call this categorical variables, allow for a classification of individuals based on some attribute or characteristic. And then quantitative variables provide the numerical measurement. All right, let's look at an example of this, distinguishing between qualitative and quantitative. So the question is, determine whether the following variables are qualitative or quantitative. Gender, qualitative. Temperature, quantitative. Number of days during the past week that a college student studied. Quantitative. Zip code. This is a tough one. Think about it. Zip code. We know zip codes are numerical, but they can't really be quantified. They're qualitative. The numbers are used to categorize areas on a map. Distinguish between discrete and continuous variables. So here's discrete. Okay, they're countable numbers starting from 0. We got 1, 2, 3, so on and so forth, all the way up. A discrete variable cannot take on every possible value between any two possible values. A continuous variable is a quantitative variable that has an infinite number of possible values. It can take on and can be measured to any desired level of accuracy. All right. So data can be divided into qualitative or quantitative values, and then if it is quantitative, it could then be broken up into either discrete variables, numerical variables, or continuous. So let's look at the difference here. The first one, as you can see, the number of heads obtained after flipping a coin. The number of heads, so you can count them. That's going to be discrete. The number of cars that arrived at McDonald's drive-through between 12 and 1. Discrete. The distance a 2019 Toyota Prius can travel in city driving conditions with a full tank of gas. That distance will be continuous. All right. It is not a nice number. It's more than likely going to be a fraction or decimal of some number. The list of observations a variable assumes is called data. Gender is a variable. The observations male and female are data. All right, there's other variables as well for gender. Qualitative data are observations corresponding to a qualitative variable. And there it is, quantitative, there are observations corresponding to a quantitative variable. And then let's divide that up into the other two, discrete data and continuous data there. All right, so let's say we have this spreadsheet of sorts, a table, and we have a lot of different information. We have countries, groups, life expectancy, population, and all this. It says identify the individuals, the variables, and the data. So the individuals in the study are the countries. The variables measured for each country are the government type, the life expectancy, and the population. And the variable government type is qualitative because it categorizes the individual. The variables life expectancy and population are quantitative. Okay. And then we also have a little bit more. The quantitative variable life expectancy is continuous because it is measured. The quantitative variable population is discrete because we count people. The observations are the data. All right. So for example, the data corresponding to the variable life expectancies are 82.3, 81.9, 81, so on and so forth. So let's go back to that table one more time. So as you can see, all right. So now we're going to look at objective 5. It says determine the level of measurement of a variable. So the first level is the nominal level. The nominal level of a variable it helps categorize it. So that's when we're dealing with, again, eye color, things that can be categorized. But they cannot be ranked. Okay, let's look at ordinal. A variable is, let's see, a variable is at the ordinal level of measurement if it has the properties of nominal. However, the naming scheme allows for the values of the variable to be arranged in a ranked or specific order. And now we have the other level here, the interval level. A variable is at the interval level of measurement if it has the properties of ordinal level of measure and the differences in the values of the variable have meaning. A value of 0 does not mean the absence of the quantity. Okay? And then also one thing you should note about the interval levels, that arithmetic operations such as addition and subtraction can be performed on values of the variable. And then we have a variable is at the ratio level of measurement if it has the properties of the interval level and the ratios of the values of the variable have meaning. A value of 0 means the absence of the quantity. Arithmetic operations such as multiplication and division can be performed on values of the variable. So here we have different variables and you need to determine the level of measurement that they would fall into, that each variable will fall into. So gender would be considered nominal. Temperature, interval. There's really no natural 0 for temperature though, now is there? The number of days during the past week that a college student studied. Ratio. Letter grade earned in your statistics class. Ordinal. All right. So now we're going to venture off into section 1.2. Observational studies versus design experiments. And there are only two different objectives in this particular section of chapter 1. Distinguish between observational study and experiment, and explain the various types of observational studies. So let's go with the first objective here. And here we have an example, and as you can see, let's just go through this example. Okay, so it says researchers wanted to determine whether there is an association between mobile phone use and brain tumors. So to do so, 791,710 middle-aged women in the UK were followed over a period of 7 years. During this time, there were 1,261 incidences of brain tumors. The researchers compared the women who never used a mobile phone to those who used a mobile phone and found no significant difference in the incidence rate of brain tumors between the two groups. All right. Researchers from the United States National Toxicology Program conducted a study to address the concern that radio frequency radiation may be associated with an increased likelihood of developing brain tumors in humans. Certainly, it is unethical to purposely expose humans to a potential carcinogen, so rats were used instead. All right. The researchers randomly assigned 90 rats to one of the three possible groups. Each of the groups were housed in the um, reverberation chamber that allowed the rats to be exposed to the RFR. Group 1 rats served as a control and were not exposed to any RFR in their chamber. And Group 2 rats were exposed to the Global System for Mobile Communication Module, RFR. And Group 3 rats were exposed to the Code Division Multiple Access CDMA modulated RFR. GSM and CDMA are the modulations primarily used in the US. The rats in group 2 and 3 were exposed to RFR using a continuous cycle of 10 minutes on exposed and 10 minutes off for a total daily exposure time of about 9 hours a day, 7 days per week, for approximately 2 years. Each chamber was maintained on a 12-hour light-dark cycle with temperature range of 72 degrees Fahrenheit, plus or minus 3 degrees. A humidity range of 50 plus or minus 15%, and with at least 10 air changes per hour. All the rats had the same access to food and water, and the researchers found low incidences of brain tumor in rats exposed to RFR for both the GSM and CDMA modulations, where there were no cases of brain tumors in the control group. However, the incidence rate was not statistically significant. In both studies, the group of the research was to determine if radio frequencies from cell phones increase the risk of contracting brain tumors. Whether or not brain cancer was contracted is the response variable. The level of cell phone usage is the exploratory variable. In research, we wish to determine how varying the amount of explanatory variable affect the values of a response variable. An observational study measures the value of the response variable without attempting to influence the value of either the response or explanatory variables. That is, in an observational study, the researcher observes the behavior of the individuals in the study without trying to influence the outcome of the study. If a researcher assigns the individuals in a study to groups, intentionally manipulates the value of an explanatory variable, and then records the value of the response variable for each individual, the researcher is conducting a designed experiment. Alright, so know the difference between an observational study and a designed experiment. Alright, there is another example here, and this example, I'm not going to read it out, but I'll just show. And now, based on what you see here, would you recommend that all seniors go out and get the flu shot? Right. So, as you can see, this could be a problem of confounding variables. Researchers wanted to determine the long-term benefits of the influenza vaccine on seniors aged 65 years or older by looking at records of over 36,000 seniors for 10 years. The seniors were divided into two groups. Group 1 were seniors who chose to get a flu vaccine shot, and Group 2 were seniors who chose not to get a flu shot. After observing the seniors for 10 years, it was determined that seniors who got the flu shots are 27% less likely to be hospitalized for pneumonia or the flu, and 48% less likely to die from the pneumonia or flu. Alright, so the problem is confounding and lurking variables as well, right? There could have been other things at play that wasn't controlled in the experiment, in the study. All right, so first, confounding in a study occurs when the effect of two or more explanatory variables are not separated. Therefore, any relation that may exist between any explanatory variable and response variable may be due to some other variable or variables not accounted for in the study. A lurking variable is an explanatory variable that was not considered in the study, but that affects the value of the response variable in the study. In addition, lurking variables are typically related to any explanatory variables considered in the study. Some of the lurking variables could have been the age, the health status, or the mobility of the senior. Even after accounting for the potential lurking variables, the authors of the study concluded that getting a flu shot is associated with a lower risk of being hospitalized or dying from the flu. Now, here's one thing to note, that observational studies do not allow a researcher to claim causation, only association. Okay, so we can say that things are associated through an observational study, but we cannot say that one has caused the other. We need an experiment in order to do that. All right, so confounding variable, here it is again. An explanatory variable that was considered in the study whose effect cannot be distinguished from a second explanatory variable. All right, let's look at that second objective now. Explain the various types of observational studies. So there's the cross-sectional, the case control, cohort studies, and we have something called a census, is a list of all individuals in a population. Web scraping or data mining is the process of extracting data from the internet. Web scraping can be used to extract data from tables or web pages and then upload the data to a file. Or web scraping can be used to create a data set of words from an online article. Sometimes you can create a web crawler and that will just search for certain things that you might be looking for. It's pretty effective. The thing about the internet is how you can get to pages through links, and the more links a web page has, the higher ranking the web page is in Google's algorithm and a lot of search engines algorithms. They rank certain web pages based on the links that they have on the page, so it's a thing. When the internet came out in the mid-90s, there was a thing called web surfing, and that's when there was no Google search engine really. There wasn't much. It was just web surfing. So you would just go to one website and hop around and surf to other websites, and eventually you would get all the information that way. But in web scraping, okay, you would need some sort of statistical programming language. Python is a real programming language that you can write code that will do this. R is another language. It's for statistics, and it has a little bit of programming in it. You can web scrape using R as well pretty effectively, and get data and organize it and format it and clean it up. And next thing you know, you can upload it into a CSV file or Excel spreadsheet file. And then from there, you can begin to explore the data. Yeah, some websites, they just have data that they can just give you. So you don't even have to pull it from the site or anything fancy like that. All right, so we're going to look at section 3 now, and this is the SRS, a simple random sampling. All right, so the main objective here is to obtain a simple random sample. So first, a random sampling, what is it? And why do we do it, right? It is the process of using chance to select individuals from a population to be included in the study, or in the sample, rather. The key to obtaining a sample representative of a population is to let chance or randomness play a role in dictating which individuals are in the sample, rather than convenience. All right, so if you do a convenience sampling, um, the results are going to be very biased, which implies meaningless, not very useful. So if you do get any associations in your data as a result of your collection, it may be to deceive or deceive people. So that's why we must random sample as much as we can. All right. So a sample of size n from a population of size big N is obtained through simple random sampling. If every possible sample of size n has an equally likely chance of occurring, the sample is then called a simple random sample. So if you can select a sample size of n from a bigger population, and every possible sample of size n has an equally likely chances of occurring, the sample is then called a simple random sample. Like, for example, if we had, again, let's take the students in the class as our population, and we needed to select 5 students for a sample. Probably the best way to do it is to put everybody's name in a hat, and the paper has to all look exactly the same, maybe a post-it or something, all of the same size. And when you place them in the hat, you shuffle them around every time. If you do that, then you pull out your, sample of 5. The truth is you had any opportunity to get any 5. It could have been any 5. And the more you do it, the more different ones you get. That's going to be a simple random sample. The more different samples that you get. All right, so the number of individuals in the sample is always less than the number of individuals in the population, obviously. So here's an example of simple random sampling. Sophia has 4 tickets to a concert. 6 of her friends, Yolanda, Michael, Kevin, Marissa, Annie, and Katie, have all expressed an interest in going to the concert. Sophia decides to randomly select 3 of her 6 friends to attend the concert. List all possible samples of size n equals 3 from a population of n equals 6. Once an individual is chosen, he or she cannot be chosen again. Comment on the likelihood of the sample containing Michael, Kevin, and Marissa. So the possible samples of size 3 are listed in the table. Okay. And we can see now that there are 20 possible samples of size 3 from the population of size 6. The term sample means that the individuals in the sample. So these are all little samples. Only one of the 20 possible sample contains Michael, Kevin, and Marissa. So there's a 1 in 20 chance that the simple random sample will contain these 3. In fact, all of the samples of size 3 have a 1 in 20 chance of occurring. All right, so there are 2 different types of samples. There's samples without replacement, and then there's samples with replacement. So after you select something, you put it back in. Like the lottery, for example, when they select those numbers, the numbers are different. The numbers do not duplicate. Once they come out, you're now sampling from a different set of numbers, a smaller set of numbers, because one of the numbers is gone. It was not replaced. Alright, so this is just an example of obtaining an SRS using a table of random numbers. There are many different techniques to do it. Even our calculator has random number functions and things like that. Okay. Here's another list here. Here they're saying that you can use technology to generate random numbers if you wanted to. So if I were to follow along with this, and let's just say I say, okay, 34 is in rand. Let me find that. So that's my random number, and now I'm going to do rand int no repetition of some set. So I'll go with, let's go back to math. Math. PRB stands for probability. Int no rep. So okay, so I actually need just rand int no rep. But inside there we're going to put 1, 5, let's see, 5. Actually, 130 and then 5. And what that's going to tell us is the lowest number, 30, is our highest number, and pull out 5 different numbers, 5 random numbers. Let's try this one more time. Rand int no rep. We did rand int no rep. And for some reason, it's not accepting it. So let's see if change the model. First, I'll store 34 in rand. Actually, I'll do it this way. And then next I'll do my lower is 1, my upper is 30. I want 5 numbers, and let's paste that. Now, I got the same numbers that they got, which means the random generator is not all that random, is it? The numbers are random, but the fact that we got the same amount of random numbers is a problem. And so that's what we use what's called a seed. And the seed is some sort of cryptographic number that we use, some formula. Um, we used a seed of 34, but in order to get a different set of random numbers from the next guy or the next computer or next calculator, we would need something to seed our calculator with a different type of number. Sometimes they use time. They convert time into some kind of number and multiply by another number, and then they'll use that seed as a random generator. All right, so there are many techniques to obtain nice random numbers, okay? Now, what if we had used a different seed? Like, what if we use 16 goes into rand? And then all of a sudden we decide to, let's see, we have an entirely different set of random numbers now. Okay. All right. Let's look at section 1.4. There are 3 different learning objectives this time. How to obtain a stratified sample, how to obtain a systemic or systematic sample, and obtain a cluster sample. So a stratified sample, and I believe this is in our notes as well. It's just obtained from separating the population into non-overlapping groups. We call those stratas. Okay, so now they're showing you how to use Minitab. We'll go through this a little faster. Here's the next one, how to obtain a systemic sample. It's obtained by selecting every kth individual from the population. K is just some random number that we're using every time. So if everybody was lined up, you would select every 3rd person or 4th person, and then that would be who you would select. It would be random, but it's different type of randomness. All right, will that have bias? Probably, but it's probably still a good way to sample. It's a good technique. So here's an example of how they decided to get a systematic sample. Every 7th customer. Okay. Here's some steps. You can see it is a process. And then once you have your number, that's how you'll pull and build your sample from there. Seems like a nice method. So what is a cluster sample? So a cluster sample is obtained by selecting all individuals within a randomly selected collection or a group of individuals. Okay, so like we could select everybody that has the zip code of 98058. Um, Here's an example of how they decided to collect a cluster sample based on the number of city blocks and where people lived. I think it's just more practical and it's easier. It's doable. One thing to note that stratified and cluster samples are different. In a stratified sample, we divide the population into two or more homogeneous groups and then obtain an SRS from each group. In a cluster sample, we divide the population into groups, obtain a simple random sample of some of the groups, and survey all the individuals in the selected groups. Now, a convenient sample is one in which the individuals in the sample are easily obtained. We know that this is suspect and biased. Results should look upon with very skepticism, very much. Self-select surveys, voluntary response surveys, those, people who tend to respond to those are very opinionated, and people who are very opinionated may think a certain way, and that's going to skew the results. We have multi-state sampling. Okay, here's a graphic of what some of them looks like. This could help in terms of thinking about the different ways that samples are coming about. All right. So now we're going to move on to 1.5, the bias in sampling. This is kind of what um, all roads lead to bias when it comes to sampling. So explain the sources of bias in sampling. That's the main objective there. If the results of the sample are not representative of the population, then the sample has bias. 3 sources of bias. Usually there's sampling bias, non-response bias, and response bias. So sampling bias it means basically that the technique used to obtain individuals to be in the sample tends to favor one part of the population over another. Here's undercoverage. Sampling bias also results due to undercoverage. Non-response bias, right, exists when individuals selected to be in the sample who do not respond to the survey have different opinions from those who do. Non-response, it just goes basically, it is what you think it is. Response bias exists when the answers on the survey do not reflect their true feelings of the respondent. Yeah, they may not be telling the truth, right? This is true. They could say whatever we want, and we can't really fact check them. Maybe they want to skew our results or behave a certain way. Types of response bias. So it turns out that there's different types. Loaded questions and The order of the questions can cause individuals to answer questions a certain way. There's a lot of manipulation in words. Um, there's something called NLP, neuro linguistic programming. Okay, and it's actually related to natural language processing too, which is a whole nother computer science type of programming that's happening at the artificial intelligence level, machine learning level. But words can control us in a lot of different ways. So um, there is a way for things to be biased. But once we become aware of this, then we are less likely to be a part of it and fall for it. All right, so here we have 1.6. Here's another section here where many different learning objectives here from the design of experiments. So you want to describe the characteristics of an experiment, explain the steps in designing an experiment, explain the completely randomized design, the matched pairs design, and also the randomized block design. So experiments is where we actually can get results. Conclusions can have repercussions, and we can say that we can infer certain things from experiments. And we can say that this variable causes the other variable to happen through an experiment. Experiments is the bread and butter of statistics. So again, I'm not going to read all this out. It's here. There's your definitions. It's pretty straightforward. Blinding is important in experiments. Okay, you're maintaining integrity and fidelity. All right. So here's the characteristics of an experiment, and there's they break it down into this Lipitor, um, is a cholesterol-lowering drug made by Pfizer, and this is what's happening. There's all the information, and one of the questions is, well, what is a placebo? What does the placebo control group means, and what do we mean if this was a double-blinded experiment, right? And so here, a placebo is a medication that looks and smells and tastes like Lipitor, but it's not. It's nothing really, right? We want to see if people are going to behave differently when they consume something. So we give it to everyone, but some people have the real thing and some people do not have the real thing. We can learn a lot from that as well. The double blind both people, the experimentators and the subjects, have no idea what's going on. They don't know who's who. They don't know who has the placebo. They're just going to treat everybody the same. This is good stuff. All right, so let's look at the steps in designing an experiment. Step one would be to identify the problem to be solved, determine the factors that affect the response variables, and then we can try to control those, determine the number of units that we're going to be using. All right, it probably also deals with the resources that you have, the amount of money that you have. So step four, we're dealing with different ways to control the factors. What about randomize, right? How would we do the randomization? There's many different ways to do that. And then you conduct the experiment. Right? We test the claim. We're going to get into this later on in the course. Objective 3, explain the completely randomized design. All right, so we have a little problem and you just break it down into the different situations here. All right, let's look at a matched pair design. As you can see here, matched pairs design. We have two variables and they are connected. All right. All right. So we went through them, the chapter 1 lecture slides, but I think now it's a good idea to kind of look at some of the problems that is on the homework. So we'll randomly select some of the homework problems and kind of just see what they're asking us and go from there. All right. Match each word or phrase with its definition. So continuous variables, quantitative variables, and you'll just put them in there depending on where they fall. That doesn't seem too bad. Yeah. Determine whether the underlying value is a parameter or a statistic. Telephone interviews of 1,502 adults 18 years of age or older found that 69% could identify the current vice president. Well, first of all, it's definitely a statistic. But which one? Is it B or C? The value statistics because it's because they are indeed a sample. Say a nice word. All right. Let's see about So there's help me solve this, there's view examples, and then there's also get more help. Um, but it seems to me that, okay, so if we wanted to skip ahead to some other problems, you click on here, and now you can move ahead. What is the population in this study, right? And they're dealing with a sample teenagers that live in North America. So it would be, the population would be teenagers who are 16 that live in North America. All right, and we'll hit check, and it is good. So the homework for that assignment seems pretty straightforward. Let's look at some more problems from, say, 1.2. Now, for problems 10 and 12, they are short answers. There's not many like that, but for this one there is. So you would just type it out, and I would grade it for you. Okay, and the grades will be synced and updated if you haven't done so just yet. All right? It'll be nice to get through uh, chapter 1. Chapter 1's a lot of reading, but it changes. We'll be doing a lot of calculations. We're going to be working on our calculators quite a bit, so statistics will change quite a bit. Okay, so you can get tons of practice, and I believe this is even mobile friendly, where you should be able to even pull this up on your cell phone as well. Let's look at a couple more questions. What does it mean when a part of a population is underrepresented? A part of the population is underrepresented when it's proportionally smaller in a sample than in its population. A part of a population is underrepresented when it is proportionally smaller. A part of the population is underrepresented when individuals selected to be in the sample who did not respond to the survey all have different opinions from those who do. This is a good question. And when they say, what does it mean when a part of the population is underrepresented? It seems like that's when you're selecting a sample that's not a good representation of the population. But when they say a part of the population is underrepresented when it is proportionally smaller in a sample than it is in its population. I like that choice. A part of a population is underrepresented when it is proportionally smaller in its population than in a sample. Um, Yeah, so like, I mean, if, well, I guess we have to think about this carefully because a sample could be underrepresented too if it wasn't selected as an SRS. But I would go with a part of the population is underrepresented when it is proportionally smaller in a sample than in its population. Let's see if it likes that, and it does. All right, so we are going to end the lecture chapter 1 video at this time. I hope this was helpful, and if you happen to have any questions on the chapter 1 problems, reach out to me and I can make a helpful video that goes over detailed solutions on any question. Talk to you soon.